Protoplanetary disks are crucial structures in the formation of planetary systems. These rotating disks of gas and dust surround young stars and provide the raw material for the birth of planets. Understanding the role of protoplanetary disks is essential for comprehending how planetary systems, including our own solar system, form and evolve. Protoplanetary disks originate from the collapse of a molecular cloud core, which leads to the formation of a protostar surrounded by a rotating disk of material. The conservation of angular momentum causes the infalling gas and dust to flatten into a disk shape. These disks typically span tens to hundreds of astronomical units and can last several million years before dissipating. The composition of protoplanetary disks includes hydrogen and helium gas, along with heavier elements and solid particles such as silicates, carbonaceous materials, and ices. These materials serve as the building blocks of planets. The disk is generally structured into distinct regions: an inner hot region, a midplane with high dust density, and an outer cold region where volatile compounds freeze onto dust grains. One of the fundamental processes in planet formation is the growth of solid bodies within the protoplanetary disk. Micron-sized dust grains within the disk collide and stick together, forming larger aggregates. Through a process known as coagulation, these particles gradually grow into millimeter-sized pebbles and then centimeter-sized rocks. As particles continue to collide and merge, they form kilometer-sized planetesimals, precursors to planets. The presence of turbulence within the disk can either facilitate or hinder this growth, depending on local conditions. Gravitational instabilities and the streaming instability, where small particles cluster due to gas drag, also play significant roles in the formation of planetesimals. The next stage in planet formation involves the accumulation of mass through core accretion. Once planetesimals grow to a critical size, they exert significant gravitational attraction on surrounding material, leading to runaway growth. This results in the formation of planetary embryos, which continue to accrete material from the disk. For terrestrial planets, core accretion primarily involves the accumulation of rocky material. In contrast, gas giants form when a massive core, typically exceeding 10 Earth masses, captures surrounding hydrogen and helium gas before the disk dissipates. This process is believed to have shaped Jupiter and Saturn in our solar system. As planets form, they interact with the surrounding disk material, creating gaps and influencing their own migration. Young planets can migrate inward or outward depending on their interactions with the disk's gas. Type 1 migration affects lower mass planets embedded in the gas, while Type 2 migration occurs when more massive planets carve gaps in the disk and migrate due to disk viscosity. The migration process plays a significant role in shaping planetary architectures, as seen in exoplanetary systems with close-in giant planets or resonant planetary configurations. The final positioning of planets depends on a complex interplay of disk dissipation, gravitational interactions, and migration forces. Protoplanetary disks do not last indefinitely. They gradually dissipate due to processes such as photoevaporation, accretion onto the central star, and planet formation. High-energy radiation from the young star ionizes and removes gas from the outer regions of the disk, leading to its eventual dispersal. Once the gas component dissipates, only solid material remains, forming a debris disk. This marks the transition from a protoplanetary disk to a mature planetary system. Understanding disk dissipation timescales is crucial for determining when and how planets can form within these disks. Protoplanetary disks serve as the foundation for planet formation, providing the necessary material and environmental conditions for planetary growth. From the initial dust aggregation to the emergence of planetesimals, planetary embryos, and fully formed planets, these disks play a dynamic and essential role. Studying protoplanetary disks, both in our own solar system's history and in extrasolar systems, provides valuable insights into the diversity of planetary systems in the universe.